Welcome to this in-depth discussion on some of the fundamental concepts in thermodynamics: state functions, path functions, intensive properties, and extensive properties. Understanding these ideas is crucial, as they form the foundation for how we analyze energy changes, material behavior, and processes in technical and scientific fields. Let's begin by considering what we mean when we talk about a system in thermodynamics. A system is a defined part of the universe under study, separated by boundaries from everything else, which we call the surroundings. To understand how a system changes or interacts with its surroundings, scientists classify the measurable quantities, called properties, in specific ways. First, let's explore the concept of state functions. A state function is a property whose value depends only on the present state of the system, not on how that state was reached. This means that regardless of the path the system took to get there, the state function's value remains the same, as long as the starting and ending conditions are identical. Imagine altitude. If you go from the bottom to the top of a mountain, your change in height is only determined by the starting and ending elevation, not whether you followed a direct route, zigzagged, or stopped along the way. Common examples of state functions in thermodynamics include internal energy, pressure, temperature, volume, and entropy. These are quantities you can describe completely if you know the current state of the system. If you return to the same state after some process, like in a complete cycle, the change in any state function is always zero. In contrast, path functions depend not only on the system's initial and final states but also on the specific process or path taken between them. Path functions measure values that are linked to the manner or steps involved in the transformation. Classic examples are heat and work. For instance, if you heat water, the total heat absorbed may differ depending on whether you heat it quickly or slowly, or if you stir while heating. Similarly, the work done in compressing a gas depends on whether you compress it slowly, rapidly, or in several stages. The value of a path function can differ for each of these scenarios, even if the final outcome in terms of temperature or volume is the same. Think of climbing a hill. While your gain in altitude, a state function, depends only on where you started and finished, the calories you burn, a path function, depend on which route you took and how strenuous it was. Thus, path functions are process-dependent. Now, let's pivot to another important classification: intensive and extensive properties. This categorization answers a different question. Does the value of a property change when we change how much material is present in the system? Intensive properties are those that do not depend on the amount or size of material in the system. They're intensities, essentially features that describe the character of the substance regardless of quantity. Examples include temperature, pressure, and density. If you cut a block of metal in half, each piece retains the same temperature and density, and the pressure inside a gas-filled tank doesn't change if you divide the gas evenly into two tanks. These properties are valuable for identifying or characterizing a material, because they're unique to the material itself, not how much of it you have. Extensive properties, on the other hand, do depend on the system's size or amount of material. They scale with system quantity. Classic extensive properties are mass, volume, internal energy, enthalpy, and heat capacity. If you double the size of the system, say, by combining two samples, you double the mass, double the volume, and double the total internal energy. These properties provide a measure of how much of something is present. Here's an interesting connection between these categories. If you take the ratio of two extensive properties, you often get an intensive property. For example, dividing mass by volume gives you density, which is intensive. Dividing total internal energy by the amount of substance gives specific internal energy, again, an intensive property. Let's bring these concepts together for clarity. State functions, like internal energy or entropy, can be either intensive or extensive. Entropy is a state function, and it's also extensive, since a bigger system has more entropy, all else equal. Temperature is a state function and is also intensive. Work and heat, which are path functions, can transfer energy between systems, but their values depend on the way you move energy, not just where you start and end. Understanding whether a property is intensive or extensive tells you whether it scales with system size, while knowing whether it's a state or path function tells you whether it only depends on the system's present state or also on how the system got there. Before we wrap up, let's try a quick mental exercise. Is pressure intensive or extensive? It's intensive, unchanged when a system is divided. Is the total mass of a system a state function or path function? It's a state function because it doesn't depend on process, it just is. Is heat an intensive or extensive property? Heat, as a form of energy transfer, is an extensive path function. It's both path-dependent and proportional to system size. In conclusion, these classifications help us systematically analyze thermodynamic problems by relating observable changes to the underlying physics and chemistry. Whether you're working on chemical engineering, physics, or practical technical projects, clear understanding of state and path functions, and intensive versus extensive properties, will help you predict system behavior, design experiments, and interpret experimental data accurately. Thank you for engaging with this foundational topic. The more you practice applying these ideas, the more intuitive they'll become in your studies and projects.